So in this video we can go over on how we can be able to analyze the ground back to ground case of the projectile motion. So now make sure that before this lesson you have gone through the actually free fall motion and even the linear kinematics, and on the same case you should also have to go through the cases of the projectile motion. Otherwise we have about 4 or 5 cases of the projectile motion that we are to look up to for the time being. So in this case, let's see on how we can be able to analyze the ground back to ground case of the projectile motion. Now let's say we have the object in that has been launched at actually this point at an angle theta with respect to the horizontal, which is the x-axis. And let's say the object has been released with initial velocity given as v, or some books they call it as v naught, of course, but that is the same. Now as the object has been released at this point, it has to move all the way along for the whole entire journey in 2 dimensions. So whichever the point, it will have the components of the speed in 2 dimensions. So we'll have the speed in 2, we'll have the velocity in 2 dimensions at whichever the point until it get landed the ground. So keep that in mind. So that's the essence behind the object moving in 2 dimensions. So which means from the point of release, or the launch point or we call it as the launch position, the object is going to move in 2 dimensions. We'll have the speed in 2 dimensions, that is x-axis as well as the y-axis, until it get back onto the ground level. So now the point of interest is, how should we be able to analyze the overall motion of the object, in this case of the projectile motion? Now keep this in mind. The highest point achieved by the object is said to be the maximum point. So this point is said to be the maximum point given as MP. And the velocity at the maximum point, it is given as 0, and which is basically denoted as Vmax, which means the velocity at the maximum point, and which is always given as 0. Keep that in mind. So let's start with the analysis of the analysis of the motion of the object, in this case of the projectile motion. So now, much as the object is moving 2 dimensions, and the analysis will be done independently. And guess what? This is the initial velocity being launched at an angle theta in this case. So what is the initial velocity along x? Because as the object has been launched at an angle, then we'll have the initial velocity along x-axis and also initial velocity along y-axis. So now the component with respect to the initial velocity along x-axis will be given as this component, that is given as Vix, which means the initial velocity along x-axis, and which is given as v cos theta. So keep that in mind. So which means initial velocity along x-axis is given as Vix, that is v cos theta. And mind you, we are to start with x-axis analysis in the x direction, and later we're going to finalize with the analysis along y-axis direction. So the initial velocity along x-axis, it is given as Vix, which is given as v cos theta, upon resolving the vector into components, rather upon resolving the velocity into components. So now, along x-axis, acceleration due to the gravity is given as well, because gravitation force is not felt along x-axis, hence the object will have the 0 acceleration. Now from the concept of the actual linear kinematics, we say that acceleration is given as the final velocity minus the initial velocity divided by time. So now whenever, should be divided by time rather. So whenever the object is having the 0 acceleration, It means we'll have 0 is equal to v minus u over t. That is the same as v is equal to. So whenever the object is moving, whenever the object is having the 0 acceleration, it means the object is moving at a constant speed. Thereby, final velocity is the same as the initial velocity. So along x-axis, what it means is that the speed does not change. So in other words, the velocity does not change. It remains the same from the perspective that acceleration to the gravity is given as 0. So which means until where the object will have to strike the ground, the velocity of the object along x-axis will be given as vfx, which is final velocity along x-axis. That will be given as also vix, that is given as v cos theta. So take note of that. So which means along x-axis speed does not change. Therefore, final velocity is the same as the initial velocity. Hence, we'll have vix being the same as vfx. That is the final velocity along x-axis. That will be given as v cos theta. So keep that in mind. Now, if this is the case, then we can conclude that it to be in this way. So now, which means the final velocity, which is vfx, it is the same as v cos theta. Mind you, since the object has been launched at this position and it will be moving in 2 dimensions, even as it will be striking the ground, will have also be in 2 dimensions. Only that the final velocity along x-axis, as the object is going to strike the ground, will be given as vfx. That means the final velocity along x-axis. So get that and up to that. So now, what is the time takes for the object to move from the launch position to where the object is going to strike the ground along x-axis? So now the time takes for the object to move from this point to this point along x-axis, it is given as the time for the whole entire journey, that is t total. So which means the time takes for the object for the whole entire journey from this point to this point, it is given as the t total. Now, since we have the velocity along x-axis, and we have the time takes and we have the time takes for the object to move along x-axis, then we can be able to have what you call the horizontal distance. That is the distance along x-axis. So now, from the formula for the displacement, we know that the displacement is given as ut plus half at squared. Of course, in the perspective of the free fall motion, we'll have AC is equal to ut minus half gd squared. Now, from the fact that the object is having the 0 acceleration along x-axis, then it means the whole of this one will be given as 0. So what it does is that we'll have the displacement is equal to u actually t. So if that's the case, then we'll have it as horizontal distance, which is the displacement, is given as vix in the times the t total, which is the time for the whole entire journey. And of course, this is the same as vix should be vfx, much as the velocity along x-axis does not change. So vfx times t total, of which this is the same as v cos theta times the t total. So this is the formula that used to have the horizontal distance along x-axis. That's the distance traveled by the object along x-axis from the launch position to where the object is going to strike the ground. So generally, horizontal distance will be given as v cos theta times the times the total time. So keep that in mind. So now this is how we analyze the motion along x-axis. So make sure that you understand about all these cases, or actually this kind of the principles behind the motion along x-axis. Now let's start in the analysis of the object, of the motion of the object along y-axis, and to see how beautiful it will be. Now, along x-axis, the object will have the initial velocity being given as vi actually y. and that will be given as v sin theta. So initial velocity will be given as viy, that is given as v sin theta. That is upon resolving this vector actually velocity into components. So which means from the point in which the object has been released, we'll have the initial velocity along y-axis, that is given as v sin theta in that way. Now, what is the time takes for the object to reach at the maximum point, that is along x-axis? So now the time is said to be the Tmax. So the time takes for the object to move from the launch position to the maximum point is said to be the Tmax. And how do we calculate that on actual? We use what you call acceleration formula. We know that final velocity is given as at plus u, where this is the final velocity acceleration, and this is the time takes, and this is the initial velocity. So now let's think of incorporating this formula with respect to the free form motion, and of the actually with respect to the free form motion, in this case of the projectile motion. So now the final velocity we are talking about will be given as Vmax. That's the velocity at the maximum point. That will be given as, now acceleration will be the acceleration due to the gravity, and that will be given as negative g. And the t we're talking about will be given as the Tmax, and the plus initial velocity along y-axis, that will be given as v sin theta. So now in this case we'll have the Tmax will be given as Vmax and minus v sin theta, and divided by, and that should be like this, and that is divided by, say, should be negative g. And of which, from the fact that Vmax is always there, it means the Tmax will be given as negative v sin theta, that divided by negative g, and of which you have to cancel this, and thereby you'll have the Tmax being given as v sin theta. So now this is the formula that we use to have the time takes for the object to move from the launching position to the maximum point, that is along x-axis. So take note of that. So by now you know how the Tmax will be calculated. In this case, that is along x-axis. It should be along y-axis rather. Now, how can you be able to have a maximum height attained by the object? That is the distance from the launch position to the maximum point, that is given as the maximum height, which is given as this. So how should you be able to have the maximum height attained by the object, which is given as that? So now the maximum height will be obtained using the equation of kinematics as well. Mind you, in the beginning I said that before this lesson, ensure that you come across the linear kinematics as well as the free form motion, because that's the concept we can have to use in the analysis, as you can see. So now the maximum height will be obtained using this formula. Vmax is equal to u squared plus 2as. Now incorporating this with respect to the free form motion, we'll have final velocity that will be given as Vmax squared is equal to initial velocity along y-axis, that will be given as v sin theta, and to the power 2 the minus 2gh. So this is the maximum height we are looking for. And let's think of having that as the substitute formula. So which means we'll have it as, now we can have it as 2gh. Now should be given as this. Let's be realistic there. So in this case we'll have it as Vmax square and minus v square sine square theta, because of this, using the laws of indices in that case, of which this is the same as now negative 2gh in that case. Now let me just have in this way. So which means we'll have it as negative 2gh being equal to Vmax square minus, now have v square should be sine square theta, and of which, since the Vmax is given as out, it means we'll have it as negative 2 GH. That will be given as negative v square and as sine square theta. So on the same case, this negative and this negative will cancel. We'll have the maximum height being given as, now have v square sine square theta divided by 2g. So this is the formula to be used whenever we are calculating the maximum height attained by the object, as you can see. So keep that in mind. And of course, the actual maximum height can also be calculated using the displacement formula. That is, displacement is equal to ut plus half AD square. Now having this in the free fall case, we'll have it as the height, this, which is given as that. The initial velocity along y-axis, we'll have it as now v sine theta times t, which is the t max. D minus, you now have g t max square. So much as we have the t max in the initial velocity along y-axis, we can be able to have the maximum height using this formula as well. So take note of that. Also, this formula can also be used. That is, the actual displacement is equal to u plus v over 2 times the t, of which this is the height, that is equal to initial velocity along y-axis. We'll have it as v sine theta and plus the final velocity, which is v max, and that divide by 2 times this being given as the t max. We'll be able to have the maximum height attained in that case. So keep that in mind. Now, how about the final velocity of the object as it strikes the ground along y-axis? So in other words, we are looking for the final velocity along actually y-axis, and for the object as it will be striking the ground, that which is given as now v a for y. So how should you have the final velocity along y-axis as the object is going to strike the ground? So now we use the formula for the acceleration. We have it as v is equal to at plus u, where this is the final velocity we're looking for, being given as v fy. That will be given as negative g. Now this will be given as t dot, that's the term text for the whole entire journey. And the plus initial velocity along y-axis, that will be given as v sine theta. So in this case, that's how you should have to understand how the actual final velocity along x-axis will be calculated. So mind you, this is actually total time. It is also the same actual total time the object will have to cover along x-axis. In other words, the time takes for the object along y-axis to strike the ground, it also be the same time the object has to cover along x-axis to strike the ground. So this t dot, it is the same t dot along x-axis. So that's how the final velocity along y-axis will be calculated. And by the way, the time it takes for the object to move from the launch position to the maximum point, which is the t max, it is the same time for the object to move from the maximum point to the landing point. So which means the t dot, it is the same as 2 times t max. So that is only for this case of the projectile motion. So the t dot, it is the same as 2 times t max. If we have t dot, then divide by 2, that is given as the t max. So take note of that. So how about now the speed or the magnitude of the speed the object will be striking the ground with? So now from the perspective that the object will be striking the ground in 2 components, then now we can be able to have the magnitude of the speed in which the object is going to strike the ground with, given as this. So we are looking for this speed in which the object is going to strike the ground with. And that will be given as The speed is given as the magnitude of now the square root of vfx square plus vfy square. In other words, we're going to have the magnitude of the components of the actually final velocities along x-axis, as well as the y-axis. And how about the direction of the landing? So that will be given as the tan inverse of, now have vfy over vfx, much as you understand about the vectors. So which is given as this angle theta. So the direction in which the object is going to strike the ground with will be given as this angle. And basically it is given as the negative angle because it is below the positive x-axis. And you even see that the landing speed will be the same as the launching speed, and even the launch angle will be the same as the actual landing angle, only that the landing angle will be given as the negative. So bear that in mind. Or even the final velocity along y-axis will also be the same as the initial velocity along y-axis, only that the final velocity along y-axis will be the negative. So take note of that. So this is how the landing angle will be calculated. So now let's talk about what you call the range. By the way, if we say a range, it is the same as the horizontal distance, but we should have to calculate the range in another orientation. By the way, horizontal distance, it is given as v cos theta and times the t-total in that case. But we know that the t-total, it is given as 2 times t-max. That is that. And we understand that the t-max has been calculated as now v sin theta over g, as you can remember in the beginning of this video. So now let's think of substituting this actual expression onto here. Now what we can have is this. So which means we'll have something like this. So have the horizontal distance, that will be given as v cos theta, and the times now 2v sin theta over g, given as that. And of course, this is the same as the horizontal distance being given as v square upon having v times v, and divide by g times 2 sin theta cos theta. So that is the same as that, of course. So it is just a matter of rearranging the parameters there, then we'll have that and as that. So using the trigonometric identity, that is double angle formula. So using the trigonometric identity of the double angle formulas, we understand that if we have, let's say, 2 sine, let's say, angle A cos, let's say, angle A, you know, this is the same as having it as sin 2 of angle A. That is the trigonometric identity of the double angle formulas. So if that's the case, then we'll have it as the horizontal distance being given as v square, now have sin 2 theta divided by the actual g. So this is now what you call a range. So which is given as v square sin 2 theta over g. So that's how the range is actually calculated in that case. So make sure that you understand about the formula analysis of this kind of the projectile motion, and that we check of the initial velocity along x and along y, the t-max, maximum height, the actually launch velocity, launch angle, and the landing velocities along x as well as the y actually components, and even the landing speed as well as the direction, and also how the range is calculated in that case. The next, we're going to analyze the other cases of the projectile motion and as we are going to look up to. So we're going to use the same concept for some points, but the analysis will be somehow different. So keep in mind that this kind of analysis will be the same in some cases of the projectile motion, but it will have some changes that we're going to experience about. So now what we are remaining with this case of the projectile motion, where the object is being released from the top down horizontally. That is, and we also have this case just a piece of the remainder. So we also have this case of the projectile motion, where the object has been released from the top at an angle, in this case to the ground. And finally we are having this case of the projectile motion, which is giving us that the object is being released from the top of the building but below the x-axis at this angle. So you can to analyze all these cases and for the upcoming videos. So take note of the way this case of the projectile motion, a ground back to ground case, has been analyzed. So next we see some typical examples on how you can be able to apply such analysis in the real problems. Thank you.